And so what I would like to do today is to give you some perspective, really not from my sea ice personality point of view, but from my climate modeling point of view. Because in terms of background, I used to be just a sea ice person, just not in a negative sense, but possibly in a more positive sense, doing my PhD here with Gray on trying to understand how salt gets out of sea ice, very fundamental research. And then I went straight from doing my PhD here on how salt gets out of sea ice. I went straight to a climate research institute, the Max-Planck-Institut for Meteorology in Hamburg in Germany. And I remember how shocked I was when I looked at their sea ice model and realized that all those processes that I looked at for three years throughout my PhD, none of them was remotely in those climate models. And so I basically got a position there to try and understand how important these kind of processes were for sea ice. And the longer I've been there, the more I've really started to understand how the climate model way of thinking works. And so what I try to do today is to transfer some of that knowledge to you. And in order to spark some discussion, maybe this presentation is a bit provocative. But I hope that we'll sort of sort things out later on. And I've called this a visit to the engine room, really, because what I would like to do is I would like to take a bit behind the scenes of what we do when we build a climate model, and how much or how little possibly we care about sea ice in doing so. And so one thing I should also mention before I start, from a mathematics point of view, one could argue that this question is ill-posed. What do climate models need sea ice for? Because climate models don't need anything. Climate models are tools, possibly a bit more complex than a hammer, but they're tools. And it really depends on what we want to use them for. If we want to use them to understand monsoon circulation around India, we might not need sea ice. But if you want to understand, for example, climate change in the Arctic, sea ice is quite crucial. And so I think the main answer to this question really is it depends very much on the question that you're asking. And so the question that I'm asking today throughout my talk really is how much sea ice do climate models need in order to get a reasonable representation of today's climate? So that's sort of the global world view that I'm taking on today. And so what I'll do today, I start giving you a brief overview of how we build a climate model. And I can tell you that really from first-hand experience, because of the past 5 to 10 years, we've built a new climate model at the Max-Planck-Institut, the ICON Earth System model, which really was starting from scratch, building an atmosphere model from scratch, building an ocean model from scratch, because it's now based on triangulars rather than on squares, making everything much more complicated. But it was really building a complete climate model out of nothing. But I'll not talk too much about that model today. I don't have too much to show from that model yet. And then based on that, I'll talk about how well sea ice must be represented in climate models. And I'll unfortunately point out that for much of that, a rather limited representation of sea ice is sufficient. And I'll try to explain why that is in point number 3. And then I end with some concluding remarks. And while I would like to leave also the sort of longer discussions for the end of the presentation, if anything is unclear in between, please put your hand up and ask in between. I hate sitting there wondering about how this works, how this is meant. So please interrupt if anything is unclear. So this is a sketch of our Earth system model we have at the Max-Planck-Institut. It consists of an atmospheric model, the EC Ham, where EC is the European Center in Reading, and Ham is Hamburg. So it's basically back in the old days, ages ago, this model was developed by these two institutions. It's the atmosphere. Then we have an ocean model, the Max-Planck-Institut ocean model. And these two exchange water, energy, and momentum. Then we have a model representing the land, JX Bach, which exchanges water, carbon, energy, and momentum with the atmosphere, and water with the ocean model. And then in the ocean model, we have a biogeochemistry component, which exchanges carbon with the atmosphere. And the ocean model is coupled to the atmosphere model through a so-called coupler. Ours is called OASIS, whereas the land model and the atmosphere model are much closer interlinked with each other. So there, things happen directly at every time step. And I'll just briefly walk you through these individual components to give you some idea of what we do there. So in our atmosphere model, as in any model component, we have a couple of fairly explicit equations that are derived from first principles that we can simulate, like the Navier-Stokes equation describing how stuff moves around, or the Clausius-Clapeyron equation describing how much water vapor we have in the atmosphere. And most importantly, and Danny was already hinting towards that, for the CS point of view, we have conservation laws. We must conserve things in our climate model, otherwise we can never have a working climate model, because we run those simulations for thousands and thousands of years, and if you lose a liter of water per day at the end of those 1,000 years, or maybe a bit longer, your ocean might be dried out. So we really, in building any model, we put extremely great emphasis on conserving stuff. So we conserve water, we conserve energy, we conserve momentum, we conserve carbon, for example. And while we can derive these things from first principles, there's a lot of things that we can't derive from first principles, simply because our grid cells are too large. And the main thing really in the atmosphere model that we have to parameterize is the formation of clouds. So our grid cells in the model, depending on what kind of setup we use, is a couple of kilometers to hundreds of kilometers wide. And somewhere within this grid cell in the atmosphere model, we do know that we have water droplets, and we do know that we have ice droplets, but we have no idea whether these water droplets are spread out over the entire grid cell, or whether they are squeezed in one corner of the grid cell, forming a cloud there. If we have clouds forming in our model at different heights, for example, let's assume we have a 50% cloud cover at high altitudes and 50% cloud cover at lower altitudes, we wouldn't know whether these 50% are directly on top of each other, giving you a total of 50% cloud coverage in the grid cell, or whether it's 100% cloud cover because the one cloud cover is just next to the other cloud cover. If we have ice droplets and water droplets in our atmosphere, we wouldn't know how close these are together, so we can't use first principle to figure out whether the water sees the lower water vapor pressure over the ice droplets to condensate on these ice droplets. So there's a lot of things in our cloud models that we can never do from first principle that we have to tune. There's also other things like the gravity wave drag parameterizations describing how gravity waves interact with the surface. The turbulent boundary layer, which explains how mixing occurs in the lower meters of the atmosphere. All these kind of things are things we can never do derived from first principles, so we have to tune those in order to get a climate state that looks reasonable. The same holds for our ocean model. A couple of things we can do explicitly. But then again, there are things that we have to parameterize. The most important thing we probably have to parameterize in most model setups that we still use is the vertical and horizontal impact of eddies. We are now moving towards a grid resolution where we can actually resolve eddies. But in the standard setups that we use to run hundreds and hundreds of years, we have to parameterize eddies using, for example, the so-called Gent-McWilliams parameterization, which simply describes how eddies mix the water within an individual grid cell depending on the slope lines of the water. But we do have some explicit stuff, like the equation of state of seawater, how dense the seawater is, knowing the density, the salinity, the pressure, and the temperature. And again, we have some very strict conservation laws. In our biogeochemistry model component, I just took this nice figure. We have all sorts of chemical stuff in the ocean, carbon dioxide, the alkalinity of the ocean, nutrients, and we try to figure out how these nutrients and the light and the oxygen, how those interact with the biology in the model to form plankton, how this plankton then sinks down, how nutrients then become deposited in the sediment, how they come out of the sediment again, how the carbon is exchanged with the atmosphere depending on the equilibrium pressure of carbon, depending on the temperature of the water and the salinity, for example. And these things are all mixed around by what happens in the ocean model. We have a land model where, as far as I know, we have very few very explicit parameterizations. It's very hard to do explicit mathematics on a 100-kilometer grid cell in biology. So most of that model really is based on parameterizations, for example, on what kind of vegetation classes we have, whether it's shrub or trees, and what kind of properties these vegetation classes have, how we treat soil moisture, because we only have 1 or 2 or 3 layers of soil moisture in our land model, how fire works, how often we have fire occurring naturally, what the statistical properties need to be of the land surface for there to be fire and stuff like that. Yes? Yeah?
Can you explain the acronym JSBOC?
I need to look it up. There's also a Mozart component in there, so I'll try to, yeah, I'll do that. And somehow this thing has stopped working for some reason. Yes. And then we have the CS model, which actually is not a model in itself, but it's part of our ocean model and part of our atmosphere model. So in the model that we've been using so far, the CS model was split between those two components, where in the atmosphere model we would do all the energy surface balances, trying to estimate at each atmospheric time step how much energy we have available to grow and melt ice. And then these cumulative fluxes would be given to the full sea ice model, which resides in the ocean model, and are then applied to the ice to actually then grow and melt. And through the ice we have a very, very simplified vertical heat transport, which is simply heat conduction. And our sea ice model in the Max-Planck-Institut Earth System Model is the simplest reasonable sea ice model you can possibly think of, which basically means that the vertical heat transport has one temperature, namely the surface temperature, and one temperature, namely another temperature, namely the bottom temperature, and everything is linear in between those 2 points. So it's a so-called zero-layer sea ice model in terms of thermodynamics. But again, as Danny pointed out, we conserve salt water energy, and I should have added momentum here. And then there are all sorts of parameterizations because stuff happens on smaller parts of our grid cell. For example, the rheology describing how much force you have to give to CS for it to move around and how fast it moves if you exert a certain force is described by the CS rheology. We use the traditional viscous plastic rheology from Hippler. Now, then you also pointed out that we have, within the grid cell, in reality, of course, you have all sorts of different thicknesses, but we are among those people who have a very, very simple ice thickness distribution in our grid cell. We only have 2 ice classes, one being ice and one being open water. And we parameterize the ice thickness as a virtual ice thickness distribution. And since we might need that later, I just briefly want to show how that works. Can you see this blackboard from the back? Yeah. So during freezing, if we look from the side, we have the ocean down here, and we might have some sea ice in there. And then at each time step, we grow a bit of this thick sea ice, and we grow some thin sea ice in the open water. So we grow some new ice here, and we grow some new ice here. But then in order to calculate how much the ice concentration is changing in that grid cell, what the parameterization does, it piles up this amount of sea ice against the existing ice to a certain thickness h. And this certain thickness h is our main tuning parameter for our sea ice model. So if this h is very large, it means that whenever we form sea ice in our open water, it's piled up to a large thickness, which means that in the next time step we have a lot of open water, and in this open water sea ice formation is very efficient. So if we have a large h, it means that we form a lot of sea ice in our model. Whereas if we have a little h, it means that this new ice is only piled up to much smaller in ice thickness, which means that the concentration is increasing faster, which then means that there's less open water, we get less sea ice formation in open water in the next time step, and we get an overall smaller sea ice volume. So that's our main tuning parameter during the freezing period, which basically parameterizes how much the freezing changes the ice thickness and how much it changes the ice concentration. And then during melting, again, we need to parameterize how much of the melting changes the ice concentration and how much it changes the thickness. And so what this virtual ice thickness distribution does there, it basically assumes that the ice thickness is distributed linearly, for example, between twice the real ice thickness and 0. And so whenever we melt some ice, so let's assume we get rid of this stuff down here, we melt away some of this bit here down here, the very thinnest ice, changing the ice concentration. And that's our second tuning parameter, that we can change the slope of the functional shape of this ratio between how much the melting works on the concentration and how much it works on the thickness. And so this is our virtual ice thickness distribution, which basically also follows the parameterization by Hippler. Then we parameterize our surface albedo with a simple Meltpond scheme, with having some snow on top there, and we also parameterize our roughness. And then once we have all these model components, we start putting them together to form a functioning global climate model. And the way this is done is usually that we first tune the individual components. So for the atmosphere model, we would, for example, prescribe the lower boundary condition, prescribe ocean temperature, prescribe land surface, and then tune the atmosphere model in a so-called AMIP setup until it gives a reasonable representation of how an atmosphere should look like. We do the same for the ocean, but upside down. We prescribe what happens in the atmosphere, the surface fluxes in the ocean, and then let the ocean model run and tune the ocean model until we get a reasonable representation of an ocean. We do the same for land, and then at the end of the day, we put all these components together, and then we tune the entire system to give a reasonable representation of the climate system. And that is done by running the model and getting plots while the model is running of about 100 parameters that we look at in the climate system. And we then tune some of these parameters that we know to function, to work on some of these output variables. And then at the end of the day, we have a system model that gives a reasonable representation of the global climate system. So this is, for example, output from our Earth system model there. Here, some fell off this graph. It's from 1860 until roughly today, where the black line is observed temperature, and the red and the blue lines are from a low resolution and a higher resolution version of our model. And the thing we usually tune when it comes to the global mean temperature is the pre-industrial global mean temperature. So we tune these numbers to be at the same level back there. But we don't tune, well, we didn't tune for these graphs here the way in which this evolved throughout the 20th century. I should also mention that for our new model version, we've now learned how to also tune the climate sensitivity. So we can no longer use the climate sensitivity as an estimate of model quality, whereas we could do this kind of graph because we didn't tune this agreement here. We could use that as an evaluation metric. And that's one of the things we're very careful with. Whenever we use a certain metric to tune our model, like the pre-industrial mean global mean temperature, we don't use that to evaluate our model, but we can use the evolution of mean temperature throughout the 20th century to evaluate our model. We also don't tune regional patterns of temperature because it would be way too complicated. So this is just an example of how the atmosphere-only model is doing in terms of regional biases of temperature compared to observations. And this is regional biases we do get in the coupled model system. And we're pretty happy with those, especially over land. We usually have fairly small biases of plus minus 1 degree. Biases are a bit larger over the ocean. And in particular, on the west coast, in the tropics, our model, as many other models, do have issues in getting the temperature right. We examine precipitation patterns again. We're quite happy with that, in that over land we have relatively small biases compared to observations of usually less than half a millimeter per day. And again, these patterns is nothing that we could tune for. We might be able to tune for something global, but we could never be able to tune anything on a regional basis. If we run our full Earth system model, where carbon is interactively simulated, we can again compare two measurements. So crosses the black stuff here is measurements. The red line is simulated CO2 in the atmosphere. And again, we are quite happy how in this entire setup with ocean biogeochemistry, the land models, trees burning, emitting CO2, taking up CO2 from the atmosphere, how all that agrees with what we observe. There are also modes of variability, for example, the Meteorology oscillation in the atmosphere, which is a 30 to 60-day period oscillation in the tropical atmosphere, where you see changes in the outgoing long-wave radiation, shown here in watts per square meter. This is from the analysis. This is from our model in a Hofmüller plot. No, it's a long lag plot, actually. And so time goes down here. And again, we're pretty happy with how this agrees with reality. In the ocean model, the main thing we really look for is the meridional overturning circulation, how ocean moves around in the ocean. Here, this is in the Atlantic. This is the stream function. We try to achieve something like 18 Sverdrup in terms of the strength of this circulation in the Atlantic Ocean here, where Sverdrup is 1 million cubic meter per second. And this is roughly what has been observed. So that is our main thing that we aim for getting right in the ocean. But of course, we also try to get meridional heat transports right, which is shown here in the Atlantic, for example, in blue. The solid line is observations. The dashed line, the dotted line are the two model versions that we're using. And the same for the global ocean model. Again, that is something that we don't really tune for, and so we can use that to evaluate our model. On the land, we would, for example, compare observations of how much trees there are in a grid cell with what the land model produces, or how much bare ground there is in the data compared to how much there is in the model. And again, we're pretty happy with how well this works out, because it basically means that we get the relationship of temperature and precipitation patterns right in most parts of the planet. In the ocean biogeochemistry, we would, for example, compare how much CO2 there is in the ocean in the observations and in the two model versions, or how much oxygen there is in the observations and in the two model versions. And so these are the kind of things we would try to evaluate. What I'd like to get to now is how important sea ice is for any of this.
Just before you move on, yeah. You said earlier, you can't tune for regional things, and I understand that. On the other hand, you look at that graph of vegetation, and I noticed that Australia is rather greener in your model than in reality. I mean, is there any way that you can sort of use that as an assessment to say what's wrong with them?
Yes, certainly. That is probably something that points towards errors in the precipitation. I'm not sure if you can really see it here. Australia, we do have issues sometimes with the precipitation in Australia, which then might be related to what happens in the atmosphere-ocean coupling to the west of Australia. So it might be related to something that happens in the ocean. And for example, some of these really, really long-standing biases here, that we have too warm water, so possibly too much evaporation, too much precipitation to the west coast of all these land masses here, is something you basically see in every coupled model, and we don't really understand how we can get rid of that. It's probably one of the longest standing, strongest bias we have in those global models.
Another question, you make sense you could actually tune in your latest version, your climate sensitivity. Is that a real tuning, or is that just saying we're tuning aerosols or tuning?
No, we tune something, but we know what we have to tune in order to get different climate sensitivities.
What observations and variables do you tune to get your freezing and melting parameters for the sea ice?
Yes, so for sea ice, the only thing we use to tune is these two parameters here, which prescribe to which thickness the ice is getting together here, and how much the concentration or the thickness change when we get melting. And what we try to achieve is, in our pre-industrial simulation, for which we have no observations whatsoever, an annual mean Arctic sea ice volume of 20,000 cubic kilometers. That number comes out of the blue. There's nothing that would justify using that number, but we've been using it for the past 15 years for our model. So whenever we do a pre-industrial climate model simulation, we try to have 20,000 cubic kilometers of sea ice in the pre-industrial simulation. And that's And we know that by changing this H here, we can either get a bit less or a bit more.
So you're only doing the Arctic?
Yeah, we only look at this magic, totally unreasonable, or possibly reasonable, but not constrained by measurements, pre-industrial CS volume in the Arctic.
So is that all the tuning in the whole global couple climate model, or do the ocean modelers also tune their bit and everything else?
No, so when it comes to the sea ice, there's only really a limited amount of what we can achieve in terms of how much we can move things around. So if the atmosphere gives us too warm in Arctic, we can do whatever we want in the CS model. We can't push it to those 20,000 cubic kilometers. And then we tell the atmosphere models we need a colder Arctic. And then they tune there. For example, that was the main difference between the CMIP 3 and the CMIP 5 model version when it comes to Arctic CS. The CS was much better in the Arctic. And that was related to a better tuning of the gravity wave drag, which then changed the atmospheric waves around Greenland, changed the heat transport into the Arctic.
So how do you guarantee that all these people doing this tuning are not, for example, looking at Australia vegetation?
Yeah, and then where at the end of the day everything comes together. When we say we need a colder Arctic, but the world is too cold everywhere else, the atmosphere will tell us we can't do much more for you, basically. And so that's the balancing, where throughout the entire institute we just get together and see what compromise we can take.
Again, it's about prioritising what your questions are. So
Exactly,
what questions
yeah,
are you want
yeah.
to answer with your model.
You see it? Good.
You not tune the albedo CS?
No, not anymore.
Oh, you did.
We did before we had the Melcom scheme, but now we have the Melcom scheme, so we don't tune that anymore because we say, well, we know the albedo of the melt point, and yeah. Good. When it comes to the importance of sea ice, there are really three things where sea ice matters. So first one being sea ice changes the heat exchange between the ocean and the atmosphere, as Danny pointed out, because it's a very good insulator. Sea ice changes the salinity structure of the ocean because as sea ice grows, it gives salinity to the underlying salt to the underlying ocean, and sea ice changes the energy balance of the atmosphere and contributes to polar amplification. And I'll just go through these three things now in explaining how important these aspects are for what I've just shown you, then what we try to achieve as an institute to get a reasonable representation of the entire climate state. So if we first look at the heat exchange between the ocean and the atmosphere, this is from an old paper by Gary Makert, 1982, simply showing for the central Arctic how for different ice thicknesses you get changes in the heat exchange between the ocean and the atmosphere of about 3 orders of magnitude, between almost 0 and 1,000 watts per square meter. And so sea ice is really, really good in limiting the heat exchange between the ocean and the atmosphere. And that is one of the things that is quite crucial in our model, but it only really is crucial in a certain area of the planet, and I've tried to illustrate that here with a simulation. Actually, for this talk, we did a couple of simulations last week with our coarse resolution models, so nothing of this is super robust, but I just want to illustrate a few points here. So we ran our coarse resolution coupled model, and we tuned stuff such that we got a lot of sea ice in the Arctic. So this is our winter sea ice cover in this particular representation. And this is our summer sea ice cover, so we have way too much sea ice in this simulation. And what happens then if we have too much sea ice, the Atlantic meridional overcirculation shuts down almost completely. So this is what I've shown before. This is how strong we have this circulation in the North Atlantic that brings heat towards the Arctic before we started the before we had got too much sea ice. And this is what happens if we have too much sea ice in our model. And we can really understand that quite easily by using this figure that Daniel also just showed, because we do have these so-called deep water formation sites where seawater would sink down from the surface to the deep ocean. And it is this thinking here which drives this North Atlantic current, the northern extension of the Gulf Stream. We do have similar sites here in the Antarctic, but what I've just shown here is related to what happens in these two regions here. And as we now get sea ice into those regions, we don't have enough heat loss anymore from the water. So the water doesn't become cold enough anymore in those regions. It doesn't become dense enough anymore. It doesn't sink anymore. And so this sinking branch here becomes weaker and weaker. And basically this overturning circulation shuts down. So this is after 400 years of simulation. We didn't have more time to run any further. But it gives you some impression of what we can achieve by having way too much sea ice in our model. And you also see that in our temperature fields, the North Atlantic becomes much, much colder in those simulations, in part, of course, because we have sea ice there, but also in part further down here because we don't transport the heat of the North Atlantic current into those regions here. You will also notice that something happens down here in the Antarctic. We haven't really looked into much detail as to what happens there, but I would assume that we have much stronger convection there because we grow more sea ice in those regions, so we bring up more warm water from the depth, giving rise to those biases here in the annual mean, but I haven't really looked at what happens there. So if we have too much sea ice, really the entire climate state becomes very way off, and we can't do that. And so one of the things we really try to avoid when we tune our model looking at sea ice is not having sea ice in regions where there shouldn't be any in those deep water formation areas. This is a very bleak picture. I apologize for that. The reason for that is that we only finished those runs on Friday and I didn't have time to redraw them. What we did here was to see how much we can change things just by tuning stuff within the sea ice model. And so the blue run, this is the sea ice volume here. It's a bit of a warm model, so we have a bit too little sea ice here anyway. So the blue line here is for 300 years the sea ice volume in the Arctic. The yellow run is a simulation where we increase the sea ice volume by tuning our parameter here. And the red one is where we decrease our sea ice volume. And so the yellow run is a run where we always had the new ice to pile up to the same thickness as the ice had in the grid cell. So that's our limit on the one side. Whereas for the red simulation here, we only had the sea ice get up to 50 centimeters thick, which usually causes fairly little sea ice volume. And so overall, we get like a 50–60% difference in total sea ice volume, which is what we can achieve by tuning this one parameter in the sea ice model, which has a strong effect on the Arctic sea ice volume, but it doesn't have an effect on basically anything else. So what is shown here is, for example, sea ice extent. You can barely tell those lines apart in excess of the internal variability that we see here. We don't really see much in changes in the meridional overturning circulation. It always hovers around 16–17 in all three simulations. We don't see much of a change in global mean air temperature. If we do that, it again hovers around our whatever 14–15 degrees centigrade. We don't see much in the outgoing shortwave radiation, even though we do have much less or much more sea ice in the Arctic. And so from that point of view, if we have less sea ice than we do have in reality, the global climate system in that setup doesn't really care too much about what happens in the Arctic, and I'll come back to that. And so excessive sea ice can substantially alter the meridional overturning circulation of the Atlantic Ocean, but too little sea ice is only a minor important on the meridional overturning circulation. And whenever we get the mock roughly right, we usually get a pretty good climate state anyway. And so in order to change something substantially in the climate system through sea ice, we really want to do something to the mock, and we can't do that by getting rid of our sea ice in the Arctic. The second thing is, where sea ice is important, is salt release into the underlying ocean. In order to understand that, I've shown here in a TS, so-called TS diagram, which is known to all oceanographers in the room, where we have the water temperature on one side, the salinity on this axis here, and those lines are lines of equal density. And what we want to focus on today is the region down here, which is cold Arctic water. And what you see is that for this very cold water, the temperature doesn't really matter too much for the density. It's almost vertical down here. But the salinity matters a whole lot for the density of the seawater. And as salt is released from sea ice, it changes the density structure of the underlying ocean. And Achim Stössel, for example, did an experiment where he simply turned off the salt release from sea ice. And what then happens to the overall ocean structure is shown here. The red line shows the temperature structure of the ocean for normal salt loss from sea ice, whereas the blue line shows the temperature structure of the ocean if we have no salt loss from the ocean, from sea ice. And you find that the model run with no salt loss from sea ice is much, much warmer than the other one. And that is because in the Southern Ocean, we no longer get deep convection bringing down cold water from the surface. And so the entire ocean of the world warms up if we don't have salt release from sea ice. And so we need salt release from sea ice, in particular in the Southern Ocean, to get anywhere near a roughly right global ocean temperature profile. The question then, of course, arises how realistic that salt release must be parameterized in our models. So we've done some studies here where Philip Brevank, PhD student in our group, has developed a very complex model of salt release of sea ice, which agrees fairly well with measurements. And we then compared the outcome of model simulations with this very complex model, with a model simulations where we simply prescribe the functional shape of the salinity profile. And what is shown here is the absolute difference in percentage compared to the complex parameterizations if we either use a simple parameterization or just prescribe the salt profile. And we find that in these parameters, like the sea ice thickness, the freshwater release from sea ice, the thermal resistance, or the enthalpy of sea ice, we get changes of about 4 or 5% if we change things in the if we use a more complex salt release scheme, which basically suggests that for most applications it's probably sufficient to just prescribe the salt release from sea ice. And so salt release from sea ice is important for a reasonable simulation of the Southern Ocean, but a prescribed salinity profile might be good enough for most purposes. And so I would argue if we want to get a better Southern Ocean, it's probably time better spent to work on resolving eddies under ice shelf circulation on an iceberg freshwater discharge, rather than putting in too complicated a parameterization of salt release from sea ice. And the third thing where sea ice is important is the heat balance of the atmosphere. So we do have all sorts of fluxes here from the atmosphere, short wave, long wave, where in particular the outgoing short wave very much depends on what the sea ice does. Now this is gone again here. And so we do see changes in albedo in the Arctic as the ice is retreating. And it has been suggested that those changes in the albedo are key to what we get in terms of sea ice in the climate model. And so Ian Eisenman published a study in 2007 where they examined how different the long wave radiation incoming fluxes were in climate models. They then examined what that would mean for the sea ice thickness in a standalone sea ice model, and they found that only by changing the long wave incoming long wave radiation across the range that you would find in climate models, they could simulate anything between 0 and 10 meters of Arctic sea ice. And so they argued that it really was the albedo that was tuned to prevent the sea ice in a model to get whatever 10, 15, 20 meters thick. But that is in a simplified standalone setup. And in response to that paper, De Wever and Elizabeth and others, I believe you were on there, yes, very rightly pointed out that in a coupled setup, if they change the albedo by, I should have written that down here, by 0.1, roughly to the range shown here, they only get a change in ice thickness from 1.95 meters to 2.50 meters. So much smaller response compared to what is found in this model here. And something similar is actually found when it comes to the overall impact of the albedo. Study published by Blackport and Kushner in 2014, where they changed the albedo of sea ice in a coupled climate model to a lower value. In the standard simulation, they had about 4 million square kilometers of Arctic sea ice in September. When they lowered the albedo, they had barely any sea ice left in summer. So by changing the albedo, they got a strong response of the sea ice. They get virtually no response of the meridional overturning circulation. So that didn't care about what the albedo was. And they got a spatially fairly limited response in other variables. For example, this is what is shown here is the change in 2-meter temperature, very much limited to what happens in the Arctic, and the change in air pressure they got from these simulations. Again, fairly small and fairly limited regionally, which strongly suggests that whatever we do to Arctic sea ice in terms of albedo doesn't really matter too much for the rest of the planet. And towards the end, I just very briefly want to point out some of the studies we've recently done to really understand the somewhat limited importance of sea ice that I've pointed out in this second part here. One study that we did in 2011 was where we used our standard simulation of how sea ice was disappearing in the future. And at various periods, we just removed all the sea ice from our model simulation, like here and here and here. And we were expecting the sea ice to remain gone forever, because by removing sea ice from the Arctic Ocean, we had very low albedo, a lot of shortwave radiation accumulating in the ocean, and we thought that we would come into a new climate state. But what happened instead, within 2 years, so we removed the sea ice, within 2 years or 3 years, the sea ice was just back to where it used to be. And so it really is the total climate state that dictates how much sea ice there should be, rather than the sea ice dictating anything to the atmosphere or the ocean in these simulations here. And the reason for why that was is that while in summer we did get much more heat flux into the Arctic Ocean, much more surface heat flux into the Arctic Ocean because the albedo was lower, most of that heat was simply released back to the atmosphere as stronger outgoing long-wave radiation. So there's a very strong negative feedback stabilizing the ice cover and bringing back the sea ice from where it used to be. Another reason for why sea ice might be of limited importance relates to the total heat transport into higher latitudes. So this is showing you here, because we do have more heat radiation from the sun at the equator. That heat needs to be transported to the poles in the ocean and in the atmosphere. And we try to figure out in CMIP5 models with all the different sea ice coverages, how these different sea ice coverages might affect this total heat transport we get into the Arctic. And what we found in this study was that, which is shown in the blue line here, in all the models the Arctic Ocean heat content has been increasing over the past few years, and it will continue to do that in the future. But then in some models, most of that increase in heat content of the Arctic Ocean was driven by increased surface heat flux from the atmosphere, whereas in some models it was mostly driven by more lateral heat influx from the ocean to the Arctic. And in some models it was a bit of both. So they didn't really agree at all as to how the heat comes into the Arctic Ocean, which is also depicted here, which is the change in the ocean heat flux, northward ocean heat flux in the models, and the change in atmospheric surface flux in the models. The dashed line here is the line that depicts the sum of these two means no change at all. But we do find some models have more ocean heat flux, but those have less atmospheric heat flux, and vice versa. But overall, the models relatively well agree on how much more heat flux there is coming to the Arctic Ocean as the climate warms. And that is something called the Bjorkness compensation, that the amount of heat flux, heat transport we get into the Arctic doesn't really depend on the transport mechanism. It doesn't matter on whether that happens in the atmosphere or in the ocean. But the total sum of this heat transport is simply given by the climate state as a whole. And due to lack of time, I'll skip that. And so basically, one of the things that we find again is that really the response of sea ice to what we do in the climate system is really dominated by negative feedbacks. And so we do have, if we have less sea ice, we do get more open water, which means that we do have a smaller albedo, so we might get less sea ice. So we do have one positive amplifying feedback. But whenever we run in a coupled mode, we have lots of negative dampening feedbacks. For example, we do have more outgoing long-wave radiation. We do have later sea ice formation, so we have less insulating snow, we get more sea ice. We have a thinner ice cover, we get a high growth rate, we get more sea ice. And these dominating negative feedbacks really are the key reason for why whatever we do to a sea ice model in our climate models doesn't really matter too much for the rest of the climate system. And one bit, because Danny mentioned it very briefly on natural variability, to give you some idea of how sensitive the climate system really is. This is work that Felix Bunzel in our group has recently done. This is just from a simulation where we try to figure out how well do we need to observe Arctic ice thickness in order to get good seasonal predictions. And so we had one standard simulation, and then we had another simulation where we had an ice thickness observation error of 10 to the minus 12 meter. and sprinkle that over the Arctic Ocean thickness field. So it's really a numerical round of error we introduced into the ice thickness there in May. And then we let the coupled model run. So at the end of May, we had a bit of ice concentration difference here, arising from this 10 to the minus 12 disturbance in the ice thickness. But by September, in these simulations, we had ice concentration differences of 60–70% in large regions of the Arctic Ocean. And the same for ice thickness. We had a meter thicker ice here, a meter thinner ice here. Simply suggesting how numerical round of errors, numerical noise changes the trajectory of the atmosphere, and how then the atmosphere can bring the CS model into completely new state. And so to conclude, what I've basically learned from my experience in the Climate Modeling Institute is that sometimes it doesn't really matter too much how realistic things are in our climate models. I think many things we've learned about how the climate system works have been derived from studies of exoplanets or land planets or something like that. And so I think the most robust findings we have from climate models are those that are related to processes. One example here from our recent study, that in the observational record we find a linear relationship between how much CO2 we have emitted into the atmosphere and how much CS there was in the Arctic. This is what we find in the observations, with a trend of 3 square meters of CS lost per ton of CO2. We do find exactly the same relationship in all climate models that we have. Exactly the same, meaning it's roughly linear also in all these models if we normalize them. Cumulative CO2 emissions against Arctic CS area seems to be linear, no matter what kind of CS model these models have. And so this linearity in the observations and in the models very strongly suggests that there must be some underlying mechanism, and it's those kind of underlying mechanisms that we can try to understand then. And what we find, for example, that no matter what the sensitivity was of the individual models, how much sea ice they lose per ton of CO2, they always found this linear relationship. And our explanation for this linearity basically boils down to the point that this linearity derives, or the slope of this linearity derives from how much the long-wave radiation in those models increases. And this is indeed what we find if we plot, for example, here, the change in increasing long-wave radiation in the model against how much sea ice it loses for 1 ton of CO2, we find a pretty strong correlation, which basically suggests if you want to get a better loss of sea ice per ton of CO2 emissions, you must get better long-wave radiation, which basically suggests that we need to get better clouds in order to get better sea ice as the main priority, rather than doing anything to the CS model, because all these different models will have completely different CS models, from our very, very simple parameterizations to the very complex ones of sea ice and size and limit. And so to summarize, the importance of CS for the climate system really mostly derives from its impact on the ocean circulation. In particular, too much CS can slow down the oceanic overturning circulation. Usually the importance of CS is overestimated in uncoupled setups because negative feedbacks dominate the CS response. And I would argue is also usually overestimated in coupled setups unless the model is retuned after changes to the CS code. Because of course, if I change something in my CS model, I might get a different sea ice. But at our climate modeling center, if we do have this new sea ice, we would usually retune our model to get a reasonable sea ice cover. And only if we can then find changes after such retuning, I would argue that those changes I've introduced into the CS code are relevant. Where changes also might mean that the model might have become more sensitive or anything like that. But I think this retuning is really crucial for a reasonable study. And finally, understanding does not require the most realistic sea ice cover, maybe even vice versa. And I haven't talked too much about that. What I often do for trying to understand what sea ice does in our climate models is I run the model lots of times. And so for that, I need a really, really, really fast model. And so the sea ice model that we have in our model is incredibly cheap. If we run our ocean model with or without sea ice, we don't really notice any difference in runtime. Whereas I do know from some other models that the sea ice models are so complicated that they sometimes are more expensive than the entire ocean model, which then is a real burden of running a model hundreds and hundreds and hundreds of times. And so depending on what you want to do, it might be advantages of having a very simple, very fast CIS model. And the second reason for why I like very simple models is that I do understand precisely what I do when I tune something. So for example, back in the days when we didn't have to have a melt-point parameterizations, we could simply tune the albedo from 0.65 to 0.67, and I would know exactly what I was doing. But now with the melt-point parameterization, you would then start tuning how much snow ice thickness distributions you would have in your grid cell. So you would basically just get the tuning parameter to a different level, making it much less direct, which makes it much harder to understand what you're actually doing. And so I believe that for understanding things, the most simple parameterizations might often be the most helpful ones because you really understand what you change. The same holds for the salt release from sea ice. If I tune the overall salt I have in sea ice, I can much more directly understand what the impact of salt from sea ice is on the ocean circulation. Whereas if I have a complicated parameterizations, it might be much harder to understand that. And very finally, I'm convinced that not everything we do as scientists needs to be directly relevant for climate change. And sea ice, for me, really is fascinating in its own right. And I sometimes wonder if it might not free us from a lot of pressure if we start really admitting that and trying also to get that out to funding agencies who are so focused on everything must be related to climate change. And I very much like what Danny said in terms of describing the relevance of my talk. I didn't capture unknown unknowns. And I believe that unknown unknowns are usually found in science not because you do something that is directly related to climate change, but because you do fundamental science. And this fundamental science, I think we must push the funding agencies to fund much more than everything needing to be related to climate change. And that's all I had to say. Thank you very much for your attention.